Hey guys, this is Chap, and so we are about to cover the last chapter for general chemistry for the year, chapter 16 on acids and bases. So pull out your notes, please. If you haven't got them, you need to go to RenWeb and print them out. I will have uploaded them for you, or I may have even emailed them to your parents. We're going to flip back and forth between the notes and the Prezi so that we can get some interesting visual aids, and you might be able to write some on here. So let's first of all start with acids. We're talking about the physical properties. Remember, physical properties are things that can be reversed, and we're not talking about acids reacting to form something else. So acids have a sour taste. Think lemon juice. They dissolve in solution to conduct an electrical current. Some of them do, and because they ionize. When they ionize just means form ions. So something like hydrogen with a +1, that's the ion, or chlorine with a -1, that's the ion. It has a charge. So this whole thing has a charge. That's the chlorine ion. That whole thing is the hydrogen ion. So some of them dissolve in solution to conduct electricity, and those are called electrolytes. Any substance that ionizes to conduct electricity is called an electrolyte. And sometimes if you sweat a lot, they talk about your electrolytes not being good, so you need to drink some kind of drink with extra electrolytes in them to balance you out. So that's what those are. Let's look at the Prezi real quick. This is the Prezi for acids and bases. Notice I have the pHs at the top. We're going to talk about pH and what that means, but the pH value, if it's 0, that's super strong acid, like hydrochloric. That's the kind of in your stomach. And then the weaker the acid, 7 is neutral. And then it turns to base. And the stronger the base, the bigger the number for the pH. And so some strong bases are like sodium hydroxide. Oven cleaner is a strong base. Bleach is a base. So this is just the pHs right here. We'll be referring to those a lot. And we'll also talk about the hydrogen ion concentration. The first thing you'll notice when you click through is the Quizlet. So you can go to the Quizlet. I don't know if I'm going to assign it or not, but you can go to the Quizlet. You need to learn these strong acids and bases. There's not like a ton of these, but you do need to know these. It'll probably be in some kind of matching section of the test. And there's also a Kahoot. If we have time, we'll play some on this Kahoot. So let's start off with the acids and bases. Acids. This is where we were in the notes. So this is any substance that ionizes to conduct electricity. So let's look at this picture. These are the ions that are produced. So this is hydrochloric acid, one of the strong ones. And notice the hydrogen ion, when it ionizes, it breaks up. So we have just the hydrogen ion by itself and the chlorine by itself. And in the past, we kind of referred to these as the charges. These are the oxidation numbers. So ions are produced. And when ions are produced down here, the plus and the minus charges from the hydrochloric acid, it allows electricity to flow through this circuit. Now, we're not going to go through electrochemistry, but just know that it would allow electricity to flow because it would be moving charges. And so we would get some charges going through this. Look there, bigger picture. And then we have acids turn blue litmus paper red. Acids turn litmus paper red. This is a picture of that. And they also react with metals to produce hydrogen gas and a salt. So this is just a picture of an acid turning the litmus paper red. We're going to write something on our notes real quick about that. So here it is, acids in red. So I would like you to add this to your notes. You put a big letter D and write acid in red. And it's just a mnemonic device. They both end in a D. To help you remember that acids turn litmus paper red. This is just to write one of the reactions from the Prezi for a chemical property for acids. So let's go back to the Prezi and see. So here we have several different acids and metals. This is magnesium metal and hydrochloric acid, and I do have some magnesium metal, so I'll probably be able to show you this one. When you put the hydrochloric acid on the metal, it's going to produce magnesium chloride, aqueous, meaning it's dissolved in the water, and it's producing this hydrogen gas. So in your notes, you need to just write, these are all single replacement reactions. Notice that the magnesium is taking the place of the hydrogen, see that, and kicking it out. So we did this before. This is the couple that are dancing. and this is, in this case, the male or the female, doesn't matter, but they push the other positive thing out. So hydrogen's by itself, the magnesium took its place. They switched partners. Well, I mean, it just basically pushed one of the partners away. So write one of these on your notes. It doesn't matter which one you choose to write. And just as an example, so it shows that the hydrogen gas is being produced. You have a metal and some sort of acid. This is sulfuric acid. Remember the sulfate ion? We're going to have to review a little bit of acid names. So adic-itis, sulfate becomes ic acids. So this is sulfate becomes sulfuric acid. So zinc and sulfuric acid produces zinc sulfate and hydrogen. Zinc and hydrochloric acid. Remember, hydrochloric is for binary acids. This is all from chapter 8, first semester. So I know that's been a long time ago. If you want to pull out your notes, that'd be good to just remembering. But you won't have a ton of naming to do. But the zinc replaces the hydrogen. And so now we have zinc chloride and the hydrogen gas again by itself. Now, we will watch this video. Let's see if we can watch it right now. Hold on. Now, I don't know if you can hear him talking, but he's talking about metals reacting with acids to produce salt and hydrogen gas. And so he has some zinc metal right here, hydrochloric acid and sulfuric acid. And he's going to put the zinc in to the two different acids, and we're going to look for bubbles. See the bubbles forming? There's a bunch of bubbles forming. All those bubbles forming are the hydrogen gas that's being produced from that reaction. I'm not going to worry about the rest part of that. So acids and bases. That brings us to bases. Okay? Now this follows along in your notes as well. Bases are the physical properties. They have a bitter taste. Coffee is bitter and tea is bitter, and so that's why we add sugar to it. And you can add salt to take away too. They feel slippery, and I will make you actually touch a little bit of sodium hydroxide to feel it. It turns red litmus paper blue, and so we're going to put a little mnemonic device on our notes about that one. I have a picture about that. So here, it turns red litmus paper blue, so it's a base. If it turned it red, it's an acid. So red to blue, base, blue base. Acid is red. And when we react an acid with a base, we form water and salt. This is a neutralization reaction. It's also a double replacement reaction. Here we have the positive and the negative, and the positive and the negative, they switch partners. The H goes with the OH to form water. The Na goes to the Cl to form salt. So double replacement reaction is also a neutralization reaction here. The H goes with the OH, the positive goes with the negative, and this positive goes with that negative to form water and KNOH. It always forms water and a salt. Water and a salt every single time. You can please write one of these reactions in for the chemical properties of a base. You can choose this one or this one. Take a moment and write that in. And when you've done that, so you may need to pause the video and move forward. Here, this is also showing you a double replacement reaction. Acids are proton donors, so it donates the hydrogen, and the OH is here as well. And then what's left over is the sodium and the chlorine. They get together and form the salt. So that's the basis. Now here's those pH values again. Acids have a very low pH. Bases have a very high pH. 7 is neutral, pure water. Blood is very close to neutral. We're going to talk about a little bit what the pH range is for blood a little bit later in our notes. Notice that each of them have a mixture of hydrogen and hydroxide ions. Hydrogen ions and hydroxide, OH ions. Hydrogen ions and hydroxide. Hydroxide and hydrogen. Okay, so that's going to bring us to this portion here. Definitions of acids and bases. Okay, so the list of I'm going to go back to the notes for a minute because we're going to get to the Arrhenius model for a moment, but I want to go back and look at the notes real quick. Okay, we did this. We got to add our mnemonic device for bases. So bases, and I'm going to write it in blue, bases turn litmus paper blue. So that's just to help you remember that. So for a list of common acids and bases, see your text or the Prezi for this chapter. So we have a lot of common acids and bases. There's some over here. I need you just mostly to memorize the strong ones. If I need you to memorize something else, I will let you know. But here's a bunch of acids over here. Now we're going to be moving to the Arrhenius model. And Arrhenius, this is aqueous. Remember, aqueous is water. So Arrhenius model is aqueous model. So we're going to be talking about things dissolved in water. The Arrhenius model is only for aqueous substances dissolved in water. Dissolved in water. All right, now in the Arrhenius models, acids release hydrogen ions. Now, one of the more complicated things I think for this chapter is just remembering the three models and what they represent. So remember that a hydrogen ion is actually a proton. Now, in a hydrogen atom, a hydrogen has one proton and one electron. When it loses its electron, all that's left is the proton. So let's just draw a picture of this for a minute. We have a proton in the hydrogen ion, and we have an atom rather, and we have one electron orbiting that proton. Okay? Remember, protons are positively charged. So this could be a model of a hydrogen atom. Hydrogen atom. You can please write this in your notes. Pause it if you need to. Okay? So that's a neutral hydrogen atom. It has one proton, that's a positive one, and one electron, that's a negative one. Now if something comes along and swipes that electron, so we're going to move it over here. If we lose the electron, okay, what's left? Well, we end up with just the proton sitting there by itself. Well, that proton has a +1 charge, and we could say this is the hydrogen has a +1 charge now. That's the hydrogen ion. And that hydrogen ion is just a proton. So notice that. A proton equals a hydrogen ion. So in the Arrhenius model, it says, remember that a hydrogen ion is a proton. In the Arrhenius model, it releases a hydrogen ion or a proton. The H plus is not stable though. So because we have this really positive thing running around, and it doesn't, remember, nature wants to try to use as little energy as possible. And what do likes do? Likes repel. That's one of the important things in chemistry. But what do opposites do? Opposites attract. So hydrogen ion is running around, it's unstable, so it bonds with water to form this thing here called a hydronium ion. There's that word, hydronium. That's an important word. And so the number of hydrogen ions is equal to the number of hydronium ions. And so these acids over here are all considered acids by this Arrhenius model because they all have hydrogens to donate. And you can look at it. In the Arrhenius model, the hydrogens are listed in the front. See all those in the front? These are Arrhenius acids. They all have hydrogens to donate. So when it donates a hydrogen ion, it's an Arrhenius acid. So you're going to see them all at the front. These are Arrhenius acids. Excuse me. Okay, I'm going to go back to the Prezi for a moment. Here I'm showing you that the hydrogen ion is a proton, that the neutral hydrogen becomes a hydrogen ion plus an electron. The electron, the E minus sign is the symbol for an electron. Here's the hydrogen ion joining to water. Now remember that water's polar. So this side, this is the oxygen side. The oxygen side of water is negative. So the positive hydrogen joins the negative side of the water to form this hydronium ion very quickly. So this is again hydrogen and water, they come together to form hydronium ion. Hydronium ion. And this is just a list of a bunch of acids, and I put those in your notes as well. Notice how all the hydrogens are at the front. For the most part, if the hydrogens are at the front, you have an Arrhenius acid. Methane, though, is not an acid. So this is one of those things to remember. Methane, CH4, is not an acid. Notice how its hydrogens are not written, how it's written on the second part, that it's not at the front. And that may help. And then also remember that NH4, ammonia, can act like an acid as well. So we're going to learn more about these. Ammonium, NH4 plus. It's the ion, ammonium. You will need your polyatomic ion charts. Again, if you don't have those, we need to get those reprinted, okay? Now we're going to talk about Arrhenius bases. An Arrhenius base is something that releases hydroxide ions. Whoops. So there, hydroxide, the OH ion is the hydroxide ion. That's in your polyatomic ion chart. You need to memorize this ion. OH ion is hydroxide ion. Weak bases are going to, notice the metals are at the front. All these are metals: aluminum, calcium, iron, ammonia, ammonium. That's not really a metal, but it is a polyatomic ion. They all have OHs. So we have a metal and an OH. Those are weak bases. OH containing compounds are not always bases, though. Ammonia is an acid. Is a base. Ammonia is not a base according to this definition. For the Arrhenius model, you have to have the OH. For the Arrhenius model, you have to have the OH. So this though is not a base, rather. This is methanol. It's got the OH in it, but that OH is called an alcohol group. It's one of the exceptions. What you're going to be looking for. So you say, well, why are the exceptions? What do I look for? You're mostly going to be looking for calcium, aluminum, iron. You're going to look for metals and then the OH. And this ammonium is one of the exceptions you should remember. But metals and the OH are going to give you those strong bases. Okay, before we get to the Bronsted-Lowry, let's go back to the notes. All right. Bases. Now there's 6 strong acids you need to memorize and 6 strong bases. And these bases and acids should be in that Prezi with the strong bases and acids. Make sure you got this is ClO4 is the perchlorate. So adic-itis, so it becomes perchloric. Hydrochloric, hydrobromic, hydroiodic, nitric, that comes from the nitrate, adic-itis. Sulfuric comes from sulfate, adic-itis. And then there, lithium hydroxide, that's a metal and an OH. Sodium hydroxide, that's a metal and an OH. Potassium hydroxide, that's a metal and an OH. Calcium hydroxide, strontium hydroxide, barium hydroxide. All of those are metals and OH groups. Those are bases. Bases release hydroxide ions. Okay? And this is just reminding you hydrogen-containing compounds are not always acids. That's the methane. And the hydrogens do not ionize. And this one is just a covalent molecule. And the hydroxide-containing compounds are not always bases, or the OH ones. This is really not a hydroxide. This is really an alcohol group. So this right here is an alcohol group. It's not an OH. That brings us to the Bronsted-Lowry model. And this model is, of the three models we're going to learn about, this is the most important one, okay? Most important. This is the one we're going to use a lot. Now, for the Arrhenius model, you're going to have to just memorize them a little bit, okay? Bronsted-Lowry, so model from 1923. I don't care about the date. I'm just putting it on there for reference. So acids are proton, remember protons are hydrogen ions, donors. Acids are proton donors, bases are proton acceptors. Acids are proton donors, bases are proton acceptors. So you got to figure out a way of memorizing that. Let's see, A, D, B, A. Well, that doesn't help a whole lot. Maybe B, A, D, A. Base, acceptors, donors, acids. I don't know. Bada. Figure out something on that one. I haven't come up with a good way of doing that. I just know it. Acids are proton donors. Bases are proton acceptors. Now, deprotonation and protonation. If you Protonate, you add it on there. If you deprotonate, you take it away. So acids are deprotonation. Deprotonation means to lose a proton or to lose that H+. Because remember, the hydrogen ion is a proton. So acids are proton donors. They deprotonate. They lose it. Like you're being dehydrated, you lose water. Bases are proton acceptors. They gain it. So that's just called protonation. Okay? Just like hydration is gaining water, protonation are gaining protons. Deprotonation is losing protons, just like dehydration is losing water. All right, so this definition expands the bases because it includes many substances without OH groups, including ammonia. Ammonia is a base. So that's the Bronsted-Lowry model for acids and bases, and they come up with something called conjugate pairs of acids and bases. The acid makes the base, and the base makes the acid. And I say that over and over again. The acid makes the base, and the base makes the acid. So this is a weak acid, and it may be a little bit more difficult to see that this is an acid because of the way that it's written. But what you always need to do is compare the two molecules. So this molecule and this molecule look the most similar. What's the only difference here? Well, this molecule has a hydrogen, and like I told you, normally the hydrogens are written at the front, and you could have written this one at the front. You sometimes can write this molecule as HCH3OO. Okay? You can write it like that. So this hydrogen is here, but there's not one there. So it lost a hydrogen from here to here. So from here to here, it loses the hydrogen. So that makes it a proton donor. So that's an acid. Loses the hydrogen, or it's a proton donor. Makes it an acid. Now then you compare the other two molecules. This is the water, and like this is the hydronium ion. Well, what's the difference between these? This one has 2 hydrogens, and this one has 3. So it gained a hydrogen. It gained an H+, or a proton. It gained a proton. Acids are proton donors. Bases are proton acceptors. So that means this had to be the base. So that's how you figure it out. You compare the two. We're going to look at some worksheets in a few minutes about Bronsted-Lowry. But before we do that, we're going to go ahead and do the Lewis model. Let me check the Prezi. Okay. Acids are proton donors, and deprotonation is losing a proton. Bases are proton acceptors. Protonation means gaining a proton. And here's a video about conjugate acid-base pairs. We will take a minute to watch this probably in class, or I may assign it to you separately. I'm not going to watch it here. And then there's a really fast, silly video here. I'm not going to watch that one right now. So here's another set of conjugate acid-base pairs. I can't write on the Prezi, but I can point to things. So if I point to this, acid makes the base, and the base makes the acid. So here, there's the water, and there's the OH. Remember that water can be written as HOH. And here's the NH3 and NH4. Those are the most alike. So you compare NH3 and NH4. You can see it went from 3 hydrogens to 4 hydrogens. So it gained a hydrogen. It is a proton acceptor. It's a base. Acid makes the base, and the base makes the acid. So the base makes the conjugate acid, and then the acid, since that's the base, that one has to be the acid. The acid makes the conjugate base. The acid here donated its hydrogen, so over here it has one less. We have 2 hydrogens here, 1 hydrogen here, so it donated a hydrogen. The acid makes the base. The base makes the acid. The acid makes the conjugate base, and the base makes the conjugate acid. What does that mean, conjugate, acid, and base? It means that now this one has 4, it could give one of them away to make, so it goes back to the 3. So it'd be now this could donate a hydrogen, a proton. And the base only has 1, so it could accept 1 more to have 2. So it'd be a proton acceptor, it's a base. So the acid made the conjugate base, the base made the conjugate acid. Okay, Lewis model here. Before we go on to that, let's go back to the notes. Is this the notes? Yeah. All right, so we're at the Lewis model. I told you about those. We're going to do some work in this worksheet in a bit. Acid makes the base makes the acid. And then the Lewis model here. This expands the definition of the acids and base even more, and it forms covalent bonds. This is the most difficult to kind of visualize, so you just need to just remember things about it. In the Lewis model, an acid can accept a pair of electrons, so it has to have one empty orbital. And a base donates a pair of electrons. So let's think about the opposites. In the Bronsted-Lowry model, the acid did what? The acid donates protons, and the base accepts protons. Well, in the Lewis model, the acid accepts electrons, and the base donates electrons. So it's kind of the opposite. Look at that. The opposite of donate is accept. The opposite of protons is electrons. Okay? Because protons are positive, electrons are negative. So in the Bronsted-Lowry model, if you remember that, the Lewis model is just the opposite. The opposite of the Bronsted-Lowry model. Let's look at the base. The base accepts. The opposite of accepts is donate. It accepts what? Protons. The opposite of protons are electrons. So memorize one of them and know and memorize the Bronsted-Lowry, because that one's important. The acid donate is a proton donor. The base is a proton acceptor. I think I've said that 20 times now in this one video. So in a Lewis model, the acid accepts protons instead of donating electrons. Accepts electrons instead of donating protons. And the base donates electrons instead of accepting protons. And then they form a covalent bond. So we have a couple of pictures right here about that. The Lewis base has a filled orbital, so that's something that it could do. Now Lewis base can donate those electrons. The Lewis acid has an empty orbital, so it fills it up, so they kind of bond together and they share those electrons. And that's really the best I can do for that, to help you understand that. Now, at the end of this first section of 16a, of the first section of the chapter, this is something you need to understand. The Arrhenius model is the smallest one. These are all subsets, and you should remember math. These are subsets. This is a subset. And this one is a subset of that one. So, if I have an acid here, like if something is an Arrhenius acid, that's the smallest one. It is also a Bronsted-Lowry acid, and it's also a Lewis acid, because it's contained within each circle. If something is let me erase this for a moment. With a bigger eraser. It sometimes is good when you're doing this to kind of color. So I do this, like, okay, these are blue. If it's contained inside the blue only, it's also contained inside the green. You see that? The blue is completely inside the green. All right, and lastly is the red. Now, if it overlaps, that means it's true for all of it. And this is going to be probably one of the things you just have to think about the most. Okay? So, if I have an acid right here, is it an Arrhenius acid? Well, no, because it's not inside the Arrhenius circle. It could be if it was right there, because right there it could be a Bronsted-Lowry acid and the Arrhenius acid. Is it a Lewis acid? Yes, because everything is inside the Lewis circle. If I have a base right here, this base is just a Lewis base. It is not a Bronsted-Lowry base, and it's not an Arrhenius base. If I have a base right here, this base is an Arrhenius base because it's inside the blue circle. It's a Bronsted-Lowry base because it's inside the green circle, and it's it's an Arrhenius base, a Bronsted-Lowry base, and a Lewis base because it's inside the red circle. So you need to memorize these circles and how they work, okay? Because this is going to be probably the tricky questions. I'm going to pause the video for. Okay, so this is worksheet 84, where we're going to practice the Bronsted-Lowry acid base. Remember, acids are proton, which are H pluses, donors. H pluses are protons. Bases are proton acceptors. All right, so here's an example. We have hydrochloric acid. It donates the H to the OH because you can look at both sides. Look at that side and that side. See, it's missing it. So that's the acid. Since that took it, that's the base, because this becomes H2O. H2O can be written as HOH. So there's the H it took, and there's the OH it started out to be. So the acid is going to make the conjugate base, and the base is going to make the conjugate acid. So let's look at these. We're going to go through. Now, number one is the self-ionization of water. We'll talk about that a little bit more when we talk about pH. So if you had something like this, you couldn't tell which one was the acid and which one was the base. You can try to just write one of them as HOH to see what happens. Okay? So let's do this. This one has 2, and over here that's 3. So did it gain or lose a hydrogen? Well, 2 is less than 3, so it gained. From here to here, it gained a hydrogen, which is a proton. So what are proton acceptors? Bases. Now look at here. We have the OH and then the H. Well, over here we just have the OH, so it lost this hydrogen. So from here to here, you compare those two. That's this proton was donated. It was given to the other guy right there. It was given to that one, so it became a 3. So this is the acid. So the base makes the conjugate acid. The acid makes the conjugate base. Now what does that mean? That means this right here is now basically an acid because it has 3 hydrogens, and it could go back to having 2, so it could give one back away. And this is now a base because it has a spot, it has a negative sign, it's ready to take a hydrogen back. Acids are proton donors, bases are proton acceptors. So let's compare number 2. We have 2 hydrogens here, and this is the other thing that looks the closest to it. It has the remaining, there's only 1 hydrogen. So did it gain a hydrogen or lose it? Well, it lost it from here to here. It lost. So that means this is the acid, and if that's the acid, then this has to be the base. And the acid makes the conjugate base, and the base makes the conjugate acid. So the acid makes the base, and the base makes the acid. All right, look at the next one. We have SO4 and SO4. Here we have 1 hydrogen. We have no hydrogens. So from here to here, we lost a hydrogen again. So that's the acid. That's the conjugate base. The acid makes the base. And now we look at the next one. We have 2 hydrogens, and now we have 3. It gained a hydrogen. So from there to there, that's the base. On one side, you'll have acid and a base. So the base makes the conjugate acid. So notice that. On this side, you have an acid and a base. So once you know one's the acid, the other one has to be the base. On the other side, you'll have a conjugate base and a conjugate acid. The acid makes the base, and the base makes the acid. All right, I'm going to have you do these 2 right here. You're going to do 4 and 5. I want you to stop the video, figure these out. You can write them down right on your notes. I want to see these written in your notes. Label the acid and the base, and the conjugate acid and the conjugate base. I want to see an acid, a base, a conjugate acid, and a conjugate base labeled somewhere on these 2 reactions. And then once you get that going, you can continue with the video. All right, I'm going to assume that's done. So let me write in the answers for you. Okay, So I wrote in the answers. Now, you could have written, and it would have been just as fine, to have called this one the conjugate base and this one the conjugate acid. And the reason is these are identical molecules. It doesn't matter. But this has to be the base because it has no hydrogen to donate. Hydrogens are positive. It doesn't want to get rid of another positive. It's negative. It wants to suck in the positive because the opposites are attracting. It wants to pull, this one has 3 hydrogens. It wants to take one of its hydrogens, which is a plus, and to put it over here to even it out and make it into this molecule H2O. So the base made the conjugate acid, and the acid made the conjugate base. Over here, this is the base because it has 3 hydrogens and it got another one to make 4. So it accepted a hydrogen. So the base made the conjugate acid. So if that's the base, this has to be the acid because you're always going to have one acid and one base on this side, one conjugate acid and one conjugate base on the other side. And so if that's the acid, it has to get rid of one of the hydrogens. It had 2. So it's now down to only 1. It was written like that. I could have written this as HOH, but this hydrogen was given away and given to this one. So the acid made the base, and the base made the acid. Okay, now this is a different way of writing and dealing with conjugate acid-base pairs. And so I'm going to go through it a little bit with you just to remind you, just to get a little more practice. Okay, so initially, we have an acid, and acids are proton donors. So it has 2 hydrogens right here, and has only 1 right there. So it donated that proton, and it left this ion. So that's the equation you're dealing with now. So once it donates something, this is really a conjugate base that it's making. Okay? So here we have 3 hydrogen. If it donates one of the hydrogens, it would be H2PO4, and it lost a hydrogen, so now it's going to have a -1 charge. And so how would I write that over here? I would say H3PO4 donates 1 hydrogen, which is a 1 + 1, to become H2PO4 with a -1. Now notice that it loses 1 + 1, so that if it loses 1, we end up with a -1 charge. It loses 1 hydrogen to have a -1 charge. Right here, we just have the conjugate base. So what can I have that would neutralize this negative sign, the fluorine with the negative sign? Well, I have to put 1 hydrogen in, because that would be the +1 and the -1. They cancel each other out. The hydrogens have the +1. So what would the equation be? Hydrofluoric acid would fall apart into the hydrogen ion and the fluorine ion. All right, so what about this one? NO3 -1. Okay, I'm going to let you try this one. So pause the video and try this one on your own. All right, so you should be going now. This has 1 negative sign. I've got to neutralize that by putting a H there. And so there's the acid. This is nitric acid. So the equation would be NHO3, or HNO3 rather, forms 1 hydrogen and the NO3 minus ion. So it donates that 1 hydrogen right there. This one donates that 1 hydrogen right there. This one donates 1 of the 3 right there. This one donates 1 of the 2 right there. So that's pretty easy. Let's think about this next one. If this is the acid, then what does its base look like? Well, it's got 2 hydrogens, so it can still donate another hydrogen. So that would be HPO4. But what would the charge be? Well, it's losing another +1. It's already a -1. If we lose another one, we become a -2. So the charge here is a -2 charge. It started off as a -1 already, and then we take another one away, so it's a -2 charge. So this formula would be H2PO4 with a negative charge. If it donates another one of the protons, it's going to be HPO4 with a -2 charge. Okay, what about water? It has 2 hydrogens. It's going to donate one of them, so it has a -1 charge, because if it gets rid of one of these hydrogens, the hydrogens are a +1 charge. So you write the equation as H plus for the hydrogen it donated, and then the OH minus for what's left over. Because if I put these back together, that's a positive 1 and a negative 1. They cancel each other out. So I want you to try number 7. Just think it through. Tricky. We already have a negative 2 charge. Now we're not going to neutralize all the way. We're just going to add 1 hydrogen to it. So what would the acid be then for this one? Pause the video for a moment and see if you can do it. Okay. If I put 1 hydrogen in, it's HSO4. Now it doesn't have a 2 minus anymore, because it did have a 2 minus, but then I added in 1 hydrogen, or I added in a plus 1. So now it has a it has a minus 1 charge. The charge here is a minus 1. It was a minus 2. Now it's just a minus 1. If I added 1 more hydrogen, it would be a 0. The total charge of the molecule would be 0. So what's the formula then? There's your acid, HSO4 minus, and if it donates 1 more proton, it becomes SO4 minus 2. Okay, now you try number 8. All right, hopefully you got it. We're going to donate this proton. So it becomes PO4. It was a minus 2. We're going to lose another one, so it's a minus 3. And so what's the total formula? HPO4 minus 2. We lose 1 more hydrogen. What's left over? PO4. But it was a negative 2, but we lost another hydrogen. So that's now a negative 3. A negative 3 charge. All right, and then ammonia, or this is ammonium. It's an ion. Ammonium. Ammonium. It's on your polyatomic ion chart. That's the acid. It has a proton to donate. It has 4 protons. We're only going to get rid of one of them, one of the H's. So NH3. Now, it's a plus 1 charge. Look at that. It's a plus 1 charge. Then I'm going to take away 1. That's going to give me a 0 charge. So I don't have a charge up here. Okay? Let me take away 1. So now it's NH4 plus. I donate 1 hydrogen. And when I subtract 1 from the plus 1, I end up with NH3, ammonia, which is neutral. All right, that's where we're going to stop with this video. We will review together in class, and you'll have a few questions. Talk to you soon.